A brief look at alkenes and alkynes. Again, they're only made of carbon and hydrogen, but they have double or triple bonds between at least one carbon. So alkenes have at least one carbon-carbon double bond, and alkynes have at least one carbon-carbon triple bond. Sorry, it's moved here. And you might have, they are called unsaturated compounds, and you might have heard about unsaturated fats, and that's what it refers. Unsaturated fats are fats where you have carbon-carbon double bonds, and when you have saturated fats, that means that the hydrogen has removed all those double bonds and you only have single bonds. So your unsaturated means your carbons are not completely saturated with hydrogen, they have doubles or triple bonds. And saturated compounds is that those carbons are fully saturated with hydrogen, they have as much hydrogen as they can possibly have. And a brief look at something called geometric isomers, or cis-trans isomers also called, or E-set isomers. You will have cis-trans, E-set, or geometric isomers. And that is when you have a double bond, because that double bond is fixed, you have the double bond and you cannot rotate those two carbons with respect to each other, you would break the double bond. It actually makes a difference where the substituents are pointing to. So for example, on this one, on molecule on the left, you have the two bromine atoms pointing towards the same side of the molecule, and here on the right hand side you have the two bromine atoms pointing towards opposite sides of the molecule. So when you are pointing at the same side of the molecule, you talk about a cis alkene, and when they are pointing at opposite sides of the molecule, you talk about a trans alkene. And again, you will see that the word cis and trans, or E and set, which is how you sometimes you would call it, set and E. It appears on the name, typically in italics, although not always. And a brief detour to talk about one specific alkene, benzene, which is what we call an aromatic compound. And what do we mean with aromatic compounds? In the examples of double bonds I show and triple bonds I show you in previous slides, the double bond and the triple bond was localized in between two particular carbons. When you have an aromatic compound, those double bonds, those electrons that make the double bond, are not localized in between two particular atoms. They are part of a larger ring. And this, the benzene is the most common or the most famous of these aromatic compounds. When you have a molecule of benzene, you do not have fixed alternated double bonds in between carbons. Those electrons are shared. Those electrons that do the double bonds are shared among those 6 carbons, and that's why typically people will draw a circle in the middle. Those electrons that make the double bond are shared equally between all the carbon atoms. They are not specifically put in a place in between two particular atoms, and that's what we call aromaticity, and that's when we talk about aromatic compounds, benzene being the most famous one. In alkyl halides, halogens, so fluorine, chlorine, bromine, or iodine, is the functional group of the molecule, and it's a useful way of converting alkanes, which are you can easily get them from petrol derivatives, into something useful. So they are much more reactive. Alkanes are not very reactive. The only thing you can really do with them is burn them or convert them into alkyl halides or haloalkanes. And those are much more interesting compounds because then you can start making other molecules out of them. Some of them are valuable not only as a compound, as a launching pad to synthesize other compounds, but they are also valuable in their own right. For example, chloroform, you might have heard about chloroform, is CHCl3. Dichloromethane, CH2, Cl2, haloethane, halotene, which is an anesthetic. Some of them are have very bad press, and for example, chlorofluorocarbons are alkyl halides, and they are involved in the depletion of the ozone layer. So you have them, you have the very useful ones with very useful commercial applications, and the not so useful ones are actually an environmental problem. The functional group in an alcohol is the OH group, and we call this hydroxyl group. They are polar organic compounds because, and that means that the bond between the carbon and the oxygen, those electrons that have been shared in the covalent bond, are not equally shared. They're mostly in the hands of the oxygen. So the bond between the carbon and the oxygen is polarized. And we remember a partial negative charge and a partial positive charge. It means the oxygen is pulling from these electrons from the bond. They can form hydrogen bonds, like what you have in DNA, etc. Like water forms hydrogen bonds, and if they are small enough, they are soluble in water. When they get many carbon atoms, they become more and more insoluble. And the most commonly known one is ethanol. Ethers has oxygen as a functional group, and an oxygen bonded to two carbons. So yes, like hydroxyl group was an oxygen, but it was an oxygen attached to a hydrogen and a carbon. In an ether, you have an oxygen in between two carbons, and actually they have the same shape as the molecule of water. They are polar compounds. Again, you have the oxygen pulling from the electrons from the bond. They cannot form hydrogen bonds. And the most common one, the most famous one, is diethyl ether. So when people talk about ether, what they mean is this particular one, diethyl ether, is this compound here. They have several ways of naming them. They're beyond the scope of these videos. The typical, the most common name tends to be diethyl ether, for example, but the proper name of the compound would be ethoxyethane. So when you see the word ether in a name, or you see the name oxy in a molecule, in an organic compound, in an organic name, that tends to indicate the presence of an ether group.